In EMTP Works, I've opened the two files that were downloaded in zip and extracted to temp/I2X. First one we'll take a look at is the wind park. It's 100 megawatts, kind of similar to the one we used on August 3rd with the change in the size, and I believe the voltage connection as well. So the wind turbines, I think, are 1.667 megawatts, so we have 60 of them. The wind turbine is under constant Q control, and it's set to put out 1 per unit power, so it's going to be a PQ bus. I changed the park transformer. I put in R is 0.01 per unit, X is 0.12 per unit, and we're going to look at the converter control using the average model. So it's not a switching level model, and it runs fairly efficiently. So I believe most of the other parameters are at their defaults. Now we go over to the other end of the circuit. There's an equivalent source. Double click on that. It's a 230 kV source. The load flow initialization is going to set the magnitude and angle. The impedance data is entered on this impedance tab. And in each phase, it is, or each sequence, it's basically 10 ohms at an angle of 85 degrees. The bus where the load flow constraint is applied is here. This load flow is connected to this point here at the terminal of the equivalent source. So the angle of the voltage behind the equivalent source is negative because it's absorbing power from the wind park. I also had to put in a small inductance here for the load flow solution, and it's only 1 milliohm, so it is insignificant compared to the 10 ohms of the source impedance. And then here's our fault. It's set up to be a 3-phase fault, but you can change the impedance if you want to. The way it's set up now is going to give 50% retained voltage at the point of connection. We can also change the number of phases involved if we want with these check boxes up here at the top. And it lasts, it's applied for 0.3 seconds in each phase. Most of the components here are actually for the Comtrade recording. And there are different ways to set this up. I would recommend, if you're new to EMTP, that you read up on the signals and the bundling and how to edit those. The way I did this is I placed the Comtrade component first. I'm going to double click on that. And knowing which channels I wanted to record, I put the identifiers here in the first column, the channel identifiers. As I described in the introductory video, these match what I want with the names to be for post-processing. I have some choices in the year of the standard. It's going to be supported, the precision of the energy data that's saved. Most of this was talked about in the introductory video, but I want to point out a couple of things. If you're not using the primary values, set this to 1. The values here are going to convert, for example, volts to kV. But you can't leave this blank. Comtrade readers expect something to be there. And likewise, the phase is optional, but you need to put something there if you're not going to really use the phase, so I chose lowercase x. Otherwise, the parameters in the output configuration file get scrambled up a little bit. The other columns there are useful information, things like the units. We may at some point, add some digital signals, but the other thing I want to do is point out this is where the configuration file is going to be saved and the ASCII data file. If you need to change this, go ahead and click those 2 buttons and change it, but use an absolute path, not a relative path. Okay, we're not going to change anything there, so I'm going to just hit cancel. The way the meters work, some of these are pretty straightforward. So there's a 3-phase current meter and a 3-phase voltage meter here. Those are getting my instantaneous voltage and currents. You'll find those under the meters. You'll also find this power meter here. I want capital P of T and capital Q of T, so it's this one here that's placed. And the other signals I'm creating with some kind of processing blocks on the schematic itself. So the three voltages, the three instantaneous voltages feed this block here, this FEU. And it's for a user-defined function, and that is under control. And I go down here, and this is FEU. So we double click on that. You can have it do like almost an arbitrary calculation. You press the help and it'll tell you what all functions are available. But I'm taking the square root, the sum of the squares of the three input signals, which happen to be the phase to neutral voltages. And so that is going to give me a pretty good approximation of the line to neutral RMS, with that signal labeled BRMS there. Another one is this control signal meter. And this is what we're using to calculate the frequency. If you remember August 3rd, we could get a PLL estimated frequency, especially since we're using the average model. The PLL is active and it can estimate the frequency for us. We really want to measure at the point of connection. So I'm basing that on one voltage, one phase voltage, and if I double click on this, I got the label instead. There we go. You can. There's another way to calculate the RMS if you wanted to, but it is set up for a frequency calculation, and I put bounds on it from 55 to 65. And also, yeah, you should put a defined initial history output signal 60. It'll make the plots nicer. Otherwise, it'll take a cycle or so for the meter to wake up, and you're going to have 0 hertz until it starts measuring an actual frequency. There are different ways to measure frequency. You can kind of mimic a real sensor if you want to, but this is going to be adequate for our purposes. Once I place the COM trade, I drag this signal bundle to the left, and it is populated with all 10 signals that I defined in the table for that COM trade recorder. And then when you bring in, for example, the voltage, the current, the RMS, any of these other signals, you'll get a dialog box that offers you the chance to connect to an existing signal. And what you want is the bundle info. These are on the left-hand column, F, IA, IB, and so forth. That's alphabetical order. That's what I originally defined as a COM trade recorder, and it gets looks like it gets to define the main name of the signal. And what it's mapped to are meters and also the writing component itself. So the last component in each row refers to a COM trade channel. So what this does in the bundle is it wires up each of the meter outputs to the COM trade recorder. And that's what we want. So I've not done anything. I think everything is been talked about. So this should be ready to go. I'm going to click run and then pause the video. So the simulation has finished, and it produced these COM trade output files. Went to the configuration files and defining all the channels and the A and B scaling factors and so forth, and then the data file is the integer values for each channel at each sample point. So I'm going to go switch to the machine model, which is a similar setup in terms of the grid. The grid impedance, has not changed. I didn't need the little inductance in here, so I didn't include that. So here's the point of connection. I've added, this is interesting to plot in the scopes view. I've added this RMS meter. This is a built-in component of EMTP, where you can measure the RMS voltages independently on each phase. So let me, since it's there, let me see if I can figure what happens when I wire this into the bundle. So I don't actually want to do anything here, but these are my three phase voltages, RMS voltages, There's no available destinations because it thinks everything is spoken for in that bundle. But if there was an available slot, then I would have it available there to click on. And this is how you, in general, wire signals into an existing bundle. I didn't accept anything there, so it undid itself, that connection. The whole infrastructure, the comm trade, and its wiring didn't change. I will look at the generator step-up unit. So we are not including magnetization, but here's 0.01 plus J.12 per unit. So delta Y transformer 20 to 230 kV, and that is probably really all we need to worry about. Now look at the machine data. Look at that fitting in the screen. So the steady state voltages are going to come from a load flow solution again. Rated line-to-line voltage, rated power. The field current, I don't think I put anything in there. It doesn't really affect much. No armature resistance. This data is fairly typical. It came from an 892 megawatt machine, but you can try different data if you wanted to, but it looks like it's in the right ballpark. It's plausible. The mechanical data, you have a choice to put in an inertia constant in seconds, which is what I did there. You can also observe things like the torque or the angle or the angular velocity. Those are all interesting as well. And you can put in wiring and external controls. We're not going to do it in this session. So I think that's all I need to worry about. The load flow solution, I put in minus 23.08 degrees. I'm going to, I guess, go ahead and run the load flow so we can compare what that did. So you can actually look at the load flow solution in the load flow web, which is here, and look at the power coming out of the PB bus. That's machine, so that's it's 100 megawatts. And the angle here for phase A is minus 23.094. So it's close to the estimate that we got from the hand calculation that only included X. Not perfect, but it's close. So we would like to have an initial estimate, of the correct voltage and angle to match the load flow. If you have a really meshed system, it can be more critical what the initialization looks like. This should be ready to go. We've looked at everything. So I'm going to click run. And this one's considerably faster, so I don't have to bother pausing the video. But looking, these are new files here. This machine.dat file, machine configuration file. Now, they should look very similar because the amount of data hasn't changed. I want to bring up for this one, we'll view the scopes. But I wanted to show the machine signals. So, for example, we can plot omega and the mechanical angle. And let's look at this in the video recording window. So you can see some oscillations of up to 30 degrees, a little more than 30 degrees in the angle. And so if you changed some reactances or machine parameters or the faulting time, the fault impedance, they could go unstable. Another thing I wanted to point out maybe is one of the currents. So let's look at So there is a significant offset there in IB. So you can see this is in amperes, but the DC offset is so high, that it barely crosses zero. And this is a real concern when you're doing transient recovery voltages to look at the generator breakers, whether they're going to see occurrence or whether they can interrupt. And if you play with the resistances in the circuit, you could make it miss occurrence zeros. At this point, we're going to go run the Python post-processing script. So again, our concrete data files are ready to go. I'll go to the Python directory where it was unzipped, and I have this notebook2.bat file. It's a convenience file. It's going to launch the Jupyter Notebook on this notebook for cplot2 for the second example session. So you see the server starting up and the window popped in, and it's going to come up. Takes a few seconds. All right. So I'm going to run these cells one at a time. The first one is Python code to import the modules that we need, some pre-unit bases. This is a convenience function to load in the concrete data from a case and expecting it to be named according to these conventions we talked about. I'm going to run this next cell to provide support for doing the plots in the browser in matplotlib. If it doesn't work that well for you, you can try commenting out, use matplotlib inline or matplotlib widget. Matplotlib notebook is working for me. If it doesn't work for you, as long as you can see the plots, you don't have to zoom this time. So this next cell is for PSCAD results import, but we're going to go to the EMTP results import, and so I want the session path to be correct. And I unzipped the files into C, temp, I2X, EMTP, and I just verified in the browser the concrete data is there. If you unzip to a different place, you should change the session path to match where your files actually are. In this case, it's reading from the wind first, and it found the 10 channels, which is great, and it's going to scale these by 1e minus 3, 1e minus 6, or just 1 in the case of frequency, just so I get it in kV, Ka, megawatts, megabars. And here it reads the same channels, but from the machine data file. Now what we're going to do is plot. This is plotting one case. This is the IBR case. So it's a wind plant. It's under control action. We see instantaneous voltages and currents. So the currents go down. This is the RMS voltage sensor, so it's a little bit wobbly at times of transition because the voltages go unbalanced and you're going to get harmonics in there. So it's only approximately correct. And this, by the way, is a kV line to neutral, so you can work it out that it gives about 50% value. These next two plots are P and Q and per unit of 100 megabars. And here's the frequency. And you see that this is the nature of the sensor, that it's updating every cycle, so you get this blocky characteristic. And again, this could be an artifact of how the measurement is done, and it could be improved. But there's a frequency sensor, and it's actually transiently going up about 60.5 hertz. So we might want to do a better job on the sensing. Take a look at that in the future case. This is plotting the machine response to the same event. And so you see, we looked in scope view at the currents. If we ran it out, plotted the whole 6 seconds, you'll see some pulsations in the currents as the machine swings. You see evidence of the swings beginning here in the P and Q plot, and the same blocky stair-step nature in the frequency signal. I can plot the two on top of each other. So you see that the RMS voltage looks the same for both cases. We're getting some differences in P and Q response, and even frequency. And so these are not, of course, not even the same technology, so it's not that they're really trying to compare responses, but just to show how it could be done in post-processing ComTrade files. I have a couple of other plots that you can make, and this just plots each channel individually. It's good for debugging purposes or maybe for more clarity to look at each channel individually. And this goes for the whole, actually 6 seconds, so you can see the whole range of how long the power oscillations take. And since the wind response had not settled either, let's take a look at that one. So there is P and Q, and we scroll over to pick up the last 6 seconds. So it is stabilizing somewhat by the time 6 seconds go by. So P is restabilizing, so is Q. So that's all we need to show for now. If you have any questions or problems, please post them on the GitHub issues site or send us an email.